7.2, we take 7.1 material and we expand upon it. So this is systems of equations in several variables. So we will focus on 3 equations and 3 variables specifically. So a system that looks a lot like this one, x plus y plus z equals 1, 2x minus 3y plus z equals 3, and negative x plus 2y minus z equals negative 5. Notice that, of course, now that we have 3 equations and 3 unknowns, it's going to be a lot more work to solve for all of those. So this is a lot harder to solve. So we'll start with a reduced problem where it's already reduced down into an easier form to solve for all 3. We'll call this triangular form, where x plus y plus z equals 1, but then I have a negative 5y minus z equals 1, so there's no x left. And then I have a negative 3/5 z is equal to negative 17/5. So in this case, there's no x or y. When I reduce it to triangular form, it becomes much easier to solve. There's a lot less work to do. So we'll start by solving the systems in triangular form, and then we'll talk about how to get them into triangular form so we can solve them easier. In order to solve a system that is already in triangular form, you just use back substitution, which is a lot like what we did when we did the substitution method. You start with the equation that only has one variable and solve for it. So for us, that was negative 3/5 z is equal to negative 17/5. And so if I multiply both sides by 5, that becomes negative 3z is equal to negative 17. So I divide by negative 3. And then I have that z is equal to 17/3. For back substitution, I then take this value and back substitute it into the other equations. Naturally, I want to pick the one that only had 2 variables, y and z, to substitute z into. So I'll substitute my z value in for z in 5y minus z is equal to 1. That was 17/3, so I then add the 17/3 to both sides. 1 is 3/3, so that makes 20/3. Negative 5y is equal to 20/3, divide both sides by negative 5, and we have that y is equal to negative 4/3. Now that we have y and z, we can substitute them both into the first equation that had x, y, and z, so x plus y plus z becomes x minus 4/3 plus 17/3 is equal to 1, and I can combine the 4/3 and the 17/3 to get 13/3. And that gets me, then I'll subtract the 13/3 from both sides to see that I have x is equal to negative 10/3. So the solution in this case, since we don't talk about 3-dimensional graphing, does correspond with an intersection of these 3 curves. However, it's not something you can graph to compare against. You just have to solve it algebraically. So your solution in this case is negative 10/3, negative 4/3, 17/3 for x, y, and z respectively. So now that we know how to solve it once it's in triangular form, it's really important to know how to reduce a full system to triangular form so that we can solve it that way. We will apply something called Gaussian elimination that allows you to reduce the terms down to triangular form. What will happen is we effectively will combine the different equations in such a way that we get rid of some of the variables. So the first thing that we want to do is eliminate all of the x's from the second and third equations. Now, I have 1x in the first, 2x in the second, and 3x in the third. So if I do a combination of the second equation and the first equation, I can get rid of the x in the second equation. So if I say that my second equation is now going to become what it currently is minus 2 of the first equation, then I can combine them. Right, 2x plus 3y minus 4z is equal to negative 3. Subtract from that 2 times x plus 2y minus z equals 1, which is 2x plus 4y minus 2z is equal to 2. Now, I can see that the 2x and the negative 2x will cancel each other, and then I have 3 minus 4y, so I have a negative y. 4 plus 2z becomes a negative 2z, and then negative 3 plus a negative 2 is negative 5. So that changes the second equation from 2x plus 3y minus 4z equals negative 3 to negative y minus 2z equals negative 5. We can do the same thing with the third equation, and replace it with itself subtracting 3 times equation 1, because I want to subtract 3x off. So 3x plus 5y plus 3z equals 4, and then subtract 3 times the first equation, which is 3x plus 6y minus 3z is equal to 3. So 3x minus 3x, those cancel. 5y minus 6y is again a negative y, and then 3z plus 3z is 6z, which gets me, is 6z. 4 minus 3 is 1. So I get the equation negative y plus 6z is equal to 1. Alright, so our new system then looks like the same first equation, because we didn't change the first one, but we changed the second one, and we changed the third one. So we now have an x plus 2y minus z equals 1, a negative y minus 2z equals negative 5, and a negative y plus 6z equals 1. Now, to get it into triangular form, I still have to eliminate this y. So what I will do is I will change equation 3 by subtracting equation 2 from equation 3. So I have negative y plus 6z equals 1, subtract the negative y minus 2z equals negative 5. So negative y plus y is 0. 6 plus 2z is 8z, and 1 plus 5 is 6. So now my new system is in triangular form. I've combined the rows to the point where I've gotten rid of most of the I've gotten rid of the x in the second equation and both the x and the y in the third equation. So I have x plus 2y minus z equals 1, negative y minus 2z equals negative 5, and 8z is equal to 6. Now we're in triangular form. We can solve it the same way with back substitution that we did the earlier example. So if 8z equals 6, I can divide both sides by 8 and see that z is equal to 3/4. Then I back substitute the z into the second equation, so negative y minus 2 times z, which is 3/4, is equal to negative 5. 2 times 3/4 is 3/2, so I add 3/2 to both sides, getting negative y is equal to negative 7/2, or y is equal to 7/2. Then I substitute both y and z into the first equation, x plus 2 times y, which is 7/2, minus z, which is 3/4, is equal to 1. Combining those two fractions, I have 25/4. So x plus 25/4 equals 1. I subtract the 25/4 from both sides to get x is equal to negative 21/4. So our solution is negative 21/4, 7/2, and 3/4. Just like in 7.1, we can also have inconsistent and dependent systems. So it's important to talk about those. They're exactly the same as they were in that section. Inconsistent means you have no solutions. Dependent means you have infinite solutions. But now that you have 3 equations, they might look a little bit different. So if I go through and I apply Gaussian elimination to my equations here, an inconsistent system, I'm going to end up with a 0 equals 1. So all of my variables cancel here, but the constants don't match. So you'll notice I end up with a 3x plus 6y minus 3z in both of these, but they cancel and get me 0. But the right-hand side, 4 minus 3 is 1, and so the constants don't match. And that tells me that I have a contradiction, just like it did in the previous problem. And that contradiction tells me there are no solutions, and the system is inconsistent. Whereas dependent will reduce in the same way, but what happens is that in this particular case, I did Gaussian elimination, and both the second and third row became exactly the same thing. And so when I continue Gaussian elimination, the new system ends up with a 0 equals 0. Now that's true, just like the 6 equals 6 in 7.1, but it doesn't allow us to determine what z is. There's no equation for z, there's just 0 equals 0. So there's no value for it, and so we have to then define the solutions, which are now infinite, because we have a dependent solution. What we do for that is we define z to equal some parameter t, and then we rewrite y and x in terms of the parameter t. So if I substitute t in for z in the second equation, I have y minus 2t equals negative 3, or y equals 2t minus 3. And then for the first equation, if I substitute both the z and the y into the first equation, then I have x is equal to z minus y, which is t minus the 2t minus 3. So that simplifies to 3 minus t, ultimately. So my solution then looks like 3 minus t for x, 2t minus 3 for y, and t for z. And I have infinite solutions because I have a dependent system. Okay? Since x, y, and z are all dependent on each other through this parameter t, then all of our solutions are infinite. I can just pick a t value, so I could pick t equals 0, and that would be one of many solutions to the original system. Application, modeling financial problems. So this is the last example. If you receive $20,000 in inheritance and you want to invest it in 3 separate accounts, one of which returns 7% per year, the second returns 9%, the third returns 12%, but you have to invest it in the 3 separate accounts, okay? You invest twice as much in the third account as you do in the second, because naturally you want to accumulate more interest if you can, but you return $2,000 in interest each year based on this model, and this is linear interest. This is not exponential, this is just linear. So you go use your I equals PRT kind of model. Set up the 3 equations for the system. The money from the first account, I'm going to use x, second is going to be y, and the third account will be z. So I know that the sum of all of the money that's inherited is $20,000, so x plus y plus z will be 20,000. And I also know the percent yield for I equals PRT. And since r is 1, it's really just the percentage times the amount of money. Sorry, time is 1 year, sorry. So it's just going to be the percentage times the amount of money that you have. So then 0.07x plus 0.09y plus 0.12z is going to equal the quantity that I receive per year, which is $2,000 by the linear model. So that gives me that. And then the last thing, the parameter that I defined here, where you're investing twice as much in 3 as you are in 2, can be defined by 2y minus z is equal to 0. Because 2y will equal z. I have twice as much money in z as I do in y. So if I multiply the amount that I put in y by 2, I should get the amount I put in 3. So that gets me my system. I notice that I have these ridiculous decimals, 0.07, 0.09, and 0.12, that are really hard to work with on their own. So I multiply the whole equation by 100 so that I can deal with just numbers and no more decimals. That will change my system to x plus y plus z is equal to 20,000. 7x plus 9y plus 12z will equal 200,000. And then I still have 2y minus z equals 0. Now I need to perform Gaussian elimination to make it a triangular form. So I will subtract 7 of the first equation from the second because there's no x in the third equation, so I don't need to do anything to that. But I do need to get rid of this 7x still. So this equation, second equation minus 7 times the first equation will reduce down to x plus y plus z equals 20,000. 2y plus 5z equals 60,000, and I still have my 2y minus z equals 0. Now, for triangular form, I have to get rid of this 2y. That's the last thing I need to do. But I have 2y in the second equation, so if I just subtract the second equation from the first, I'll get rid of that y. So once I do that, I'll have x plus y plus z equals 20,000, 2y plus 5z equals 60,000, and negative 6z is equal to negative 60,000. That is my triangular form system. Now to solve for that, right, we start with the bottom one where we have negative 6z equals negative 60,000, divide both sides by negative 6. And we have that z will be $10,000. So $10,000, half of that money is going into the highest interest account. Then I back substitute the 10,000 in for z into the second equation. 2y plus 5 times 10,000 equals 60,000. 2y plus 50,000 is what that turns into, equals 60,000. Subtract the 50,000 from both sides, so I have 2y is equal to 10,000. Divide both sides by 2 to get y is equal to 5,000. So 10,000 goes in the highest one, 5,000 goes in the middle one. How much goes in the other one? So x plus y plus z is 20,000, so x plus 5,000 plus 10,000 equals 20,000. The sum of 5 and 10 is 15, so I subtract the 15,000 from both sides, and I'm left with x equals $5,000. So 5,000 will go in account 1, 5,000 will go in account 2, and 10,000 will go in account 3 in order to get linear interest of 2,000 per year. Okay, please let me know if you have any questions.